In this video, we're going to look at how to calculate the vapor pressure of a solution compared to that of a pure solvent. So of course, the vapor pressure is defined as the partial pressure of a gas in equilibrium with liquid at constant temperature. And under the same conditions, the vapor pressure of a solution is going to be lower than the vapor pressure of an equal volume of the pure solvent. So solutions have lower vapor pressures than the solvent would. But how do we calculate the vapor pressure for a solution? Well, to do that, we need to first of all know what kind of solute are we dealing with. Are we dealing with a non-volatile solute or a volatile solute? Well, a non-volatile solute is a solute that does not evaporate, and so therefore the solute does not contribute to the vapor pressure. So an example of a non-volatile solute would be something like an ionic compound or some solid solute that is dissolved in a liquid such as water. Also, we have to know if it is a volatile solute. A volatile solute would be some solute that will evaporate, and so therefore it does contribute to the vapor pressure of the solution. So perhaps if we dissolved an organic liquid in water, so maybe we dissolve methanol or ethanol or ammonia in water, these would be examples of volatile solutes because they do evaporate to some extent and will therefore affect the vapor pressure of our solution. So let's start by looking at how to calculate the vapor pressure if our solute is non-volatile. So to calculate the vapor pressure when we have a non-volatile solute, we use something called Raoult's law. Raoult's law, as you can see here, allows us to calculate the vapor pressure of the solution. And to do that, we need to know the vapor pressure of the pure solvent. So what would the vapor pressure of the solvent be if there was nothing dissolved in it? And we multiply the vapor pressure of the solvent times the mole fraction of the solvent in the solution. So let's take a look at the mole fraction a little bit more closely. The mole fraction of the solvent is equal to the moles of solvent divided by the total moles making up the solution. We can restate this as you see here. The mole fraction of the solvent is equal to the moles of solvent divided by the moles of the solute plus the moles of the solvent. So this gives us the total moles of our solution. Now there's one other thing we have to take into account. If our solute is an electrolyte, remember, electrolytes will dissociate when they're put into a solvent, such as water. So we also have to take into account how much of our solute will dissociate. So we have to rewrite the mole fraction as you see here. The mole fraction of the solvent is equal to the moles of the solvent divided by the moles of the solute times I. We'll define that in just a second as the Hoff factor, plus the moles of the solvent. So this I is what we call the Hoff factor. The Hoff factor is important because colligative properties like vapor pressure depend on the total amount of dissolved particles. So if you put an electrolyte into water, it's going to dissociate. So we have to take into account the dissociation of an ionic compound in our solution. So let's look at our Hoff factor and define it a little more closely, a little more exactly. Our I, the Hoff factor, is equal to the moles of particles in solution divided by the moles of solute dissolved. The Hoff factor for non-electrolytes is equal to 1 because non-electrolytes don't dissociate. So for every 1 mole of a non-electrolyte that you put in solution, you get only 1 mole of particles since there's no dissociation. However, for ionic compounds, the Van't Hoff factor, the moles of ions formed, depends on the degree of dissociation. So the Van't Hoff factor for ionic compounds depends on how many moles of ions are formed. So let me give you a couple of examples to help illustrate that. Let's say that our solute that we dissolved in water was sodium chloride. For every 1 mole of sodium chloride that we put in solution, we're going to produce 1 mole of sodium and 1 mole of chloride. So for every 1 mole of sodium chloride that we dissolve, we're going to get 2 moles of ions or 2 moles of particles. So ideally, assuming we get 100% dissociation, the Van't Hoff factor for sodium chloride would be 2. It just tells us how many particles we would get or how much dissociation we would get. Now the Van't Hoff factor ideally would be 2. However, the experimental value for sodium chloride, the Van't Hoff factor, is 1.9. So it's a little less than 2, indicating that sodium chloride does not quite dissociate 100%. What if magnesium chloride was our solute? Well, let's look at the Van't Hoff factor for magnesium chloride. For every 1 mole of magnesium chloride that we put in solution, we would get 1 mole of magnesium cations and 2 moles of anions. So the Van't Hoff factor for every 1 mole of magnesium chloride that we put into solution, we would get 3 moles of particles, or we would expect to get 3 moles of particles or ions. So the Van't Hoff factor ideally for magnesium chloride would be 3. So magnesium chloride predicted would be 3, and experimentally it's close, it's 2.7. Again, it's a little less because we don't get complete dissociation. So the Van't Hoff factor is a correction factor, if you will, which allows us to take into account the amount of dissociation, which is very, very important when we're dealing with colligative properties. So take a look at this problem dealing with vapor pressure. Pause the video and see if you can solve for the vapor pressure of this glucose solution. Okay, so here we're given that glucose is a non-volatile, non-electrolyte. So our formula that we're going to use, the vapor pressure of our solution, is equal to the vapor pressure of the pure solvent, in this case water, times the mole fraction of the solvent. The vapor pressure of pure water is given, and we have that here, times the mole fraction of our solvent. We have 15 moles of our solvent divided by the total moles. We have 1 mole of glucose plus 15 moles of our water, so total of 16 moles. The Van't Hoff factor for glucose is 1, so if we multiply, take that into account, again, it doesn't change our moles of our solute. So overall, we would get 22.3 millimeters of mercury for our solution. And notice that the vapor pressure of our solution is less than the vapor pressure of the pure solvent, which is what we'd expect as our colligative property. So pause the video again and try to solve for the vapor pressure of a sodium chloride solution under similar conditions. Okay, so for this one, again, we have a very similar problem, but our solute is sodium chloride, which is ionic, and so therefore we do have some degree of dissociation, and we have to account for that using the Van't Hoff factor. So we use the same formula, essentially. We take the vapor pressure of our pure solvent, and we multiply it times the mole fraction of the solvent. We have 15 moles of water divided by the total moles of our particles, if you will. So we have 1 mole of sodium chloride, and then we multiply that times the Van't Hoff factor, because for every 1 mole of sodium chloride, we're going to get 1.9 moles of particles. And we're going to add to that the 15 moles of our water to get the total moles. Here, our answer, we get 21.1 millimeters of mercury. So again, the vapor pressure is lowered compared to the pure solvent, but also think back to the previous problem. With the previous problem, our vapor pressure was 22.3 for the solution. Here, it's 21.1. Notice that the vapor pressure is lower for the sodium chloride solutions because we have more moles of particles in solution. The more moles of particles you have, the lower the vapor pressure. Again, that's what a colligative property is. So let's go on and take a look at how to determine the vapor pressure for a solution if we have a volatile solute, something that will evaporate. So the vapor pressure for a solution containing a volatile solute can be calculated using Dalton's law of partial pressures. Dalton's law tells us that the total vapor pressure is equal to the sum of the partial pressures of each component, or the partial pressure of our solvent plus the partial pressure of the solute. So our P total, that's the vapor pressure of the solution. PA, that's the vapor pressure of component A, perhaps that's our solvent. And the partial pressure of B, that's the vapor pressure of component B, perhaps the solute. So we can also combine our Dalton's law of partial pressures with Raoult's law. So here we get the vapor pressure of the solution is equal to the partial pressure of component A times the mole fraction of A plus the partial pressure of B times the mole fraction of B. So let's take a look at a problem where we're asked to calculate the vapor pressure of a solution where our solute is a volatile liquid. Pause the video, read through the question, and see if you can solve it. So in this problem, we are mixing benzene with toluene, and as we're told, both substances are volatile liquids. So because we're making a solution where both substances are volatile, we want to use the following equation where the vapor pressure of our solution is equal to the vapor pressure of benzene times the mole fraction of benzene plus the vapor pressure of toluene times the mole fraction of toluene. So let's take a look at the numbers here. Our vapor pressure is going to be 96 millimeters of mercury, that's given, and the mole fraction of benzene, we take the moles of benzene divided by the total moles. Now we don't have to worry about Van Hoff factor here because both substances are volatile and they're not, they're organic molecules, so they do not dissociate, and so our Van Hoff factor is 1. We're going to add to that the vapor pressure of pure toluene times the mole fraction of toluene, again with the moles of toluene on top divided by our total moles. So we solve these numbers, we plug them in, and we solve. We should get 69 millimeters of mercury as our final answer. So be sure that you can solve problems involving vapor pressure where we have non-volatile and volatile solutes.